Hello, everyone. Good morning, good afternoon, or good evening. Thank you for joining today's session on preparing for rapid DNA in the station. My name is Elizabeth Kwok, and I'm a Global Market Development Manager for the Human Identification Team at Thermo Fisher Scientific. Today, I'm delighted to have two of our expert rapid DNA scientists from Thermo Fisher joining me. Mark Danus, a Senior Technical Application Scientist, and Joe Chang, a Senior Product Application Specialist. Mark and Joe today will be discussing the developmental validation results of the Applied Biosystems RapidHIT ID system, the accepted usage of a validated rapid DNA system in an accredited forensics laboratory, as well as identify tips and tricks for designing a rapid DNA validation plan. Thank you, Mark and Joe, for joining us and imparting your insights. Before we get started on the presentation, a few things to note for the audience. You'll have a chance to ask questions throughout the session by typing into the box in the lower left corner. We'll be collecting them, and at the end of Mark and Joe's presentation, we'll answer questions with the time we have left. Also, a PDF of Mark and Joe's presentation will be available for download under the Event Resources tab during this live event and in on-demand replay. Lastly, there will be a brief survey at the end of our session. We would greatly appreciate you take the time to fill out. With that, I'd like to introduce our first speaker for today, Mark Danus, a Senior Technical Application Scientist within the Forensic Science Application Group of the Human Identification Team at Thermo Fisher Scientific, leading the development validation of the Applied Biosystems RapidHIT ID system. Prior to joining the Human Identification Team in 2010, Mark was previously the technical leader and laboratory manager at DNA SI Labs. During his time there, Mark managed technical operations for the Lotus project, providing local DNA database services directly to law enforcement. Mark began his career in forensics in 2003 at another private laboratory in Baltimore, Maryland, performing contract DNA analysis casework for local police agencies. Before working in the field of forensics DNA analysis, Mark began his career at Celera Genomics. Mark holds a Bachelor of Science in Biology and a Master of Science in Forensics Science degree from Townsend University. Without further ado, Mark, please take it away.
Thank you for that introduction, Liz. Hello and welcome to all of our attendees joining the webinar today. Before I begin on today's subject, however, I'd like to address the fact that while I have the privilege of sharing the work with you today, the Applied Biosystems RapidHIT ID is a result of the tireless efforts of an entire HID Thermo Fisher Scientific team of dedicated scientists, engineers, and research professionals. With that, let's begin on our journey of discussing tropospheric suspended condensate abatement pertaining to expedited short tandem repeat DNA analysis systems, or more simply put, as demystifying the Applied Biosystems RapidHIT ID validation. I didn't create that prior alternate title slide to be intentionally glib, but based on some of the eye rolls that I'm feeling through the phone right now, I don't know that I succeeded, and it may have, in fact, after all, been glib. But I chose to include that to address the fact that with appropriate levels of testing and assessment, the RapidHIT ID validation may not have to be as complex as one might think. I think it's important to highlight at the end of the day, this is still a CE system performing analysis of a direct amplification STR kit. Following the completion of today's discussion, I hope to overcome any potential feelings of analysis paralysis that you might have. In today's discussion, I'll be providing an overview of that validation testing, and we'll call out some of the studies that we performed in concordance, sensitivity, mixture detection, and contamination. And then we're going to look at some of the balance metrics, threshold analysis, stutter analysis, pull-up analysis, calculations. And then finally, we have a precision study to cover. And then last but not least, I have included some example data to share from the validation. As an overview, we performed the testing on 7 different Applied Biosystems RapidHIT ID instruments. We evaluated 11 primary cartridges throughout the testing. Testing was completed on over 500 buccal swab samples collected with Puritan 3-inch sterile cotton swabs with the semi-flexible polystyrene handles, and run on the RapidHIT ID ACE Global Filer Express sample cartridges. We had a 99.6 run completion rate in this study. The 0.4% failure rate was due to 2 sample cartridges that failed to generate .FSA files. The first study that I'm going to cover today was that concordance study. In the concordance study, we evaluated 564 buccal swab samples. These were collected from approximately 100 unique contributors, and the comparison data was run on 3130 and 3500 XL genetic analyzers. In this study, we found that we had a 99.8 sample concordance rate. This sample concordance rate was measured against those called alleles in the samples. Therefore, artifacts such as stutter were not included in this evaluation, as well as any partial results. So we didn't negatively score a concordance result where something like maybe you had one allele at TPOX drop below detection threshold. We didn't count that against the called allele total. We did, however, see one single non-concordant result due to an out-of-bin allele call, or an OB, as you see here in the bottom of the slide at SE33. This single call is why we ended up at 99.8%, and this allele designation upon review was able to be resolved when analyzed with a different alternate allelic ladder. And it is also important to note that this sample was appropriately flagged in the expert system for review. The next study that we evaluated was sensitivity. For sensitivity, we took a more practical approach to how laboratories would be using this system. Because of the fact that there's no quantitation step ahead of a rapid DNA type system, we decided that it would be best to attempt to define a sensitivity series in such a manner that took quant out of consideration. So using a practical approach, we came up with the idea to test 1, 5, 10, and 20 swab passes or swipes. A swipe or pass is defined as one unilateral swabbing motion upon sampling. So, for example, for our 5 swipes or passes, I am going up, down, and then up one more final time for a total of 5 swipes. We assessed this over a course of 4 different instruments, and the results indicated that 15 of 16 samples yielded complete profiles. One sample had a dropout event at THO1, where one of the sister alleles dropped below the analytical threshold. The surviving sister allele, however, was below our stochastic threshold and was flagged as such appropriately for profile review. At the bottom of the slide here, you'll see the metrics of those performances for the average peak heights measured in RFU, average peak height ratio for our autosomal loci. So, not unexpectedly, the more swipes or passes that you make, you get a higher RFU value. Additionally, PHR increases as well, not unexpectedly. However, it is important to note that even at one pass, we have an average PHR of 82%. The next couple slides just demonstrate those DNA profiles from the 1, 5, 10, and 20 pass series. So this is an example of 1 pass, 5 passes, you see RFU increasing, 10 passes, and then finally at 20. So at 20, you can also see that there's no system saturation occurring. The next study that we chose to highlight was the mixture detection ability of the system. In this study, we looked at a mixture of 2 contributors at a ratio of 1 to 10 parts saliva to saliva mixture. SWGDAM requirements dictate that a simplified mixture study may assist a databasing laboratory recognize the presence of mixture or contamination. So that was the purpose of running this study in the RapidHIT ID system validation, was to prove our ability to detect those mixtures. And as you see here, from the gene marker screenshot, we are successfully detecting a 1 to 10 saliva to saliva mixture in this sample. The red flags are indicating more than 2 alleles at any loci, and then the yellow flags are indicating potential imbalance issues, which would all be expected in a mixture type sample. So the system was correctly flagging mixtures. The next study undertaken was a contamination study. In this study, we ran negative sample controls following all allelic ladders and our high quantity sensitivity series samples. This is just one representative electropherogram from gene marker of that negative control testing. And you can see that in the below and in all the other data, we had no allele calls above the analytical threshold that was selected for analysis. The next topic to discuss are the balance metrics or measurements used that we came up with or calculated in this validation study. This slide on the left-hand side highlights intracolor balance calculations, as well as signal variability calculations. And on the right-hand side, you see a summary PHR table. Intracolor balance is, we calculated this by taking the mean peak height per color over the total mean peak height of the sample. So in a perfectly balanced profile, you would expect all of the values for the different colors to be 1. And as you see in the left-hand column, for intracolor balance, they are fairly balanced, and it is within expectations and is showing good performance around that value, perfect value of 1. Intracolor balance on the far right-hand column was calculated as the ratio of the mean peak height of the lowest intensity marker over the mean peak height of the highest intensity marker of the same dye channel. And so you see that for intracolor balance, most of our values vary from 38 to 42%. And not unexpectedly, this is most often the ratio of the lowest, it's the ratio of the highest molecular weight loci over the lowest molecular weight loci, and a typical pattern that you'd see in a direct amplification system. On the right-hand side of the slide, as mentioned, these are our peak height ratios that we observed for all the different loci. The left-hand column is the minimum PHR, middle column representing the maximum PHR value, and then the right-hand column, you see the mean PHR for each locus. These PHRs were calculated without the presence of any filtering turned on. And so for our mean PHRs, you can see that probably not unexpectedly, we have SE33 has the lowest mean PHR at 0.8, and then that goes up to the highest, which is 0.9 at D2S441. That being covered, the next thing I want to discuss is analytical threshold calculation. The analytical threshold was calculated on a per locus basis using receiver operator characteristic analysis to determine the RFU value where our false positive rate is dropping to 0% for those peaks that are falling in bin, or AKA allele calls. Only the false positive calls related to noise were considered here. So any calls due to die artifacts or other artifacts such as pull-up, stutter, -A, or spikes were not included in this evaluation. So on this slide, you just see a representative example of what a ROC curve would look like for an example D3 locus. You can see that our false positive rate drops to 0 at the 94 RFU value in this highlighted example. This approach was described in the 2012 FSIG publication you see at the bottom of your screen. Similarly, we also evaluated stochastic threshold in addition to analytical threshold. The stochastic threshold settings we chose were calculated on a per locus basis using a method that was highlighted in the advanced topics in forensic DNA typing for interpretation. That STR per locus multiplier was set to be calculated by using the reciprocal of the average PHR minus 3 standard deviations. We then rounded this value to the nearest 0.5. For our haploid loci, we chose to leave the stochastic threshold set at the AT, or analytical threshold, and then the stochastic threshold for those stochastic threshold multipliers that resulted in a value less than 2, we ultimately decided to use a value of 2 for that multiplicative factor. So those loci would be 2 times the analytical threshold. So summarizing all of the thresholds that we've applied in the system, we have the analytical threshold that I described was going to be calculated as that receiver operator characteristic curve on a per locus basis. Our stochastic threshold, which is also calculated on a per locus basis, based on that multiplier of the analytical threshold that was defined by that reciprocal of average PHR minus 3 standard deviations. Next, we have a series of filters. Our stutter, global filter, and locus-specific filter were all set to 20%. And then for the values between loci or between markers, the minimum intensity value set there for what is defined in gene marker as an OL, or if you're more familiar with GeneMapper IDX, these would be OMRs, that would be a 30 RFU limit. And then finally, for PHR, we set the PHR flag to be 50%. So when we look at the threshold summary on this slide, you'll see that in the third column, we have chosen to adopt 50 RFU as the minimum value for our analytical threshold in this study. And we adopted 50 RFU to filter out some of those artifacts that I've referred to previously on this slide, where I was talking about rock analysis, where I discussed that we only performed rock analysis or included those artifact peaks that fell in the allele bins themselves that could result in a false positive call. So when you evaluate other allele noise that would potentially come over that rock value that would have to be clicked off or otherwise interpreted when reviewing a profile, we determined that 50 RFU was the best value to use for analysis purposes. So those values, though, above that minimum 50, included the TPOX locus, where you see a value of 84 RFU as the minimum peak height detection threshold. Y-indel was at 74. D2S441, we see it at 68 RFU value. Moving to the next column is that stochastic threshold multiplier factor that we just discussed on the prior slides. So you see the majority of those are set at 2, which was our minimum value. Haploid loci, as discussed, are set at 1 for the Y-indel and DYS391 markers. And then those where we used the true values that we calculated include TPOX and D2, which you see at, that's D2S1338 at the bottom, that you see at 2.5. And then SE33, we calculated a multiplicative factor of 3 for application to the stochastic threshold. So not unsurprisingly, due to the fact that this stochastic threshold multiplier factor is a result of PHR, these with the higher ST factor are your higher molecular weight loci. So the next column next to that is that actual stochastic threshold value now. And you can see that the stochastic multiplier factor in the prior column has now been applied to the AT in this column, and the resulting output of the stochastic threshold column there indicates that calculation. And then finally, the final column on the slide is the percent filter that we previously discussed on the immediately prior slide. Next, I want to discuss with you our stutter evaluation. We turned off any filters when we calculated all the stutter percentages that you see on the right-hand side. It won't escape your attention that in some instances we are seeing a higher than our 20% filter that we've applied previously to data analysis in several circumstances. However, due to that fact, even due to that fact, we do see that there were only 11 out of 564 samples exhibited non-filtered stutter above that 20% threshold. This resulted in no unflagged drop-in alleles attributable to stutter, and 100% of those samples with stutter above threshold were appropriately flagged by the expert system. This next slide is just one example of stutter. So you see here that at the D12 locus, magnified on the right-hand side of the slide, the 17 allele prior to the 18 allele. And it's likely that this isn't purely the result of stutter. You probably have some pull-up effect coming off of the adjacent 12 allele in the adjacent GI channel at the D13 locus. But this does highlight for you the fact that we have identified this as a peak in a stutter position and appropriately flagged it for review. The next metric that we looked at was pull-up. Without any filters applied, we calculated the spectral pull-up on average of all peaks to be 2.6%. 10 of our 564 samples exhibited pull-up above our thresholds. Once again, similar to stutter, no unflagged drop-in allele calls could be attributable to pull-up, and 100% of those samples with pull-up above threshold were appropriately flagged by the system. And similar to stutter, I also now have a pull-up example that I'm sharing on the screen. And in this example, you see that the D2S44110 allele is pulling up into the adjacent dye channel at the Y-indel locus, where you see a OB or out of bin call in the green dye channel. And once again, similar to stutter, this is being appropriately flagged by the system. The final study to review today is that precision study. In our precision study, we ran 5 Global Filer Express control or allelic ladder cartridges across 5 different instruments. All 25 ladders were passed in the GeneMarker HID genotyping software version 2.95, and the standard deviations for all 5 of those instruments were calculated to be less than 0.14 base pairs. This is important to note, as below 0.167 base pairs leads you to resolution when applying a 3 standard deviation, leads you to achieving 0.5 base pair resolution when applying 3 standard deviations. So that was really important to stay below that 0.167 standard deviation. On the next slide, we can see those precision graphs of those 5 different ladders run on the 5 different systems indicated at the top left of each graph. Overall, so what we're looking at here is each allele call, the standard deviation for each allele call in the allelic ladder. Overall, the values are very tight. For instrument 262, you do see that the standard deviation is a little bit greater there, but it is still below that 0.167 number of importance that I provided. And as you see, the top end of that graph indicates 0.14. So we're still achieving that ability to detect a 0.5 base pair difference at 3 standard deviations. Next, in the slide deck, I just wanted to highlight some examples of profiles generated during this validation. The first example here is just showing a complete non-flagged profile that would have been passed by the expert system. Similarly, the second profile is also another passing example of a DNA profile achieved by the RapidHIT ID system GFE ACE cartridge. Our third example is our first flagged example. Here we see that at TPOX, we have some potential dropout. That looks like the sister allele here has dropped below the analytical threshold. The other sister allele at the 11 allele designation has been called. However, it's been flagged as being below that stochastic threshold, indicating there is the potential for dropout there. So in this case, the stochastic threshold behaved appropriately and did signal potential dropout that does, in fact, exist here. This profile represents the presence of another flag. In this scenario, this sample flagged due to a discordant result between DYS391, the Y-indel, and amylogenin. We see that the 11 peak at TPOX generated a pull-up peak in the adjacent green dye channel at the DYS locus. Due to the fact that this was the only haploid marker call that was in disagreement with the amylogenin result, this sample also appropriately flagged in the system for analyst review. This slide represents another flag being fired in the system or a profile designated for review. Here we see another full profile. However, at SE33, the PHR flag was fired, and hence the 27.2 allele call at SE33 being flagged for being under that 50% PHR value. As indicated, this sample then would also proceed to analyst review. The next sample is also a complete profile here that we see. Unflagged would have been passed by the expert system. And then finally, our final example, we see another example of a pull-up peak into a haploid marker. This time it's Y-indel being pulled up from D2S441. And once again, the system has appropriately flagged this for review due to the fact that the result does not agree with the other haploid marker as well as amylogenin. So this one, once again, was also appropriately flagged for analyst review. So in summary of the validations studies that we completed, included that concordance study, that sensitivity study, mixture detection study, and contamination study, assessing parameters of balance metrics, threshold and filtering analysis, as well as pull-up and stutter evaluations, and finally, the precision study. So I hope today that my portion of the presentation helped to take away potentially some of that analysis paralysis or uncertainty you may be feeling around your own RapidHIT ID system validation. And thank you for your time, and looking forward to any questions that I can help answer.
All right, thanks, Mark. We learned a great deal about the Applied Biosystems RapidHIT ID system developmental validation. A reminder to the audience, we're collecting questions and we'll answer as many questions as we can at the end of Joe's presentation. So moving forward, our next presenter for today is Joe Chang, a Senior Product Application Specialist with Thermo Fisher Scientific, currently focused on developing human identification applications on Applied Biosystems RapidHIT and next-generation sequencing platforms. With over 10 years of R&D experience in system engineering and design, Joe specializes in complete systems, including Arcturus laser capture microdissection, solid NGS platform, and precision ID on Iron Torrent PGM and S5 systems and Converge. Prior to system design, he began his career designing pilot laboratories for reagent manufacturing. Joe holds a Bachelor of Science degree in Chemical Engineering from the University of California, Berkeley. With that, I'll turn it over to Joe.
Thank you, Liz, for the introduction. Good morning, good afternoon, good evening, everyone. I am Joe Chang, and next few slides will go over how to implement the system with the data that Mark had just presented to you in the lab. So as a quick reminder, going over what we just talked about, the systems and scope for this talk are the Applied Biosystems RapidHIT ID system, or the RHID, the RapidHIT ACE Global Filer Express cartridges, as well as using the single source buccal sample types on a cotton swab. This is just the same slide that Mark had presented earlier in this webinar. This is just a quick reminder of what we will be going through for the rest of this section. So as Mark has mentioned, the validation overview that our team has tirelessly worked on was across developing a system using Global Filer Express chemistries and ran plenty of buccal samples on Puritan swabs. So what does this mean for a laboratory when they're trying to implement a rapid system? In general, there are two types of laboratories that will be running these rapid systems. There's the central core DNA forensic laboratories, as well as potentially law enforcement agencies that could potentially run the system. This could include booking stations, as well as the borders. As a high-level overview, Human Identification Professional Services offers a few validation packages for rapid technologies. This is a high-level overview of the validations that are available. There's the full validation, which is similar to what our team has performed internally at a smaller scale. So you performed tests similar to what we did, like accuracy, as well as check the system performance of the system. We also do precision, sensitivity, and as well as contamination tests. For performance checks, it's even lighter testing and validation if for labs that want to boost either the throughput of the lab or run it as an intended rapid system. And similarly for law enforcement agencies, there's also a performance check as well as an instrument evaluation to evaluate the system for the law enforcement agencies. Now, all of these packages include training as well as a report to go over the details of the validation. This slide here goes over more details of the offerings that are provided. Similarly to what we performed during development, a validation would include all the classic studies that we see in the standard CE-STR test. So validation would include contamination tests, thresholding tests to ensure that the set thresholds that has been established are accurate, sensitivity and stochastic across how the laboratory collects buccal samples, precision to make sure that the base precision is correct, accuracy with genotypes, mixture performance of the system, and any known and non-probative samples that the lab may also run. For the performance check, it's just a lighter validation with lesser samples to make sure that the system coincides with the previously validated instrument that's in your lab, as well as another offering called the performance check with the teachback. This is more catered towards the law enforcement agencies that may need a little bit of feedback on the performance of their system. Lastly, there's also an evaluation for labs who want to dabble and try out the system before going forward with a full validation or performance check. And with those validations, the quality assurance standards have been updated. This was released a couple months ago and will be in effect next year in July 2020, which includes some verbiage on rapid DNA. I won't go over all the details of the update, but the high-level overview is what is the difference between validation and performance check. And the key takeaway with Forensic Standard 8.6 is that if an instrument will be used with human interaction, if any human interaction needed to perform any data analysis, then the system needs to be validated. If the system is going to be used as intended, out of the box, running cartridges, running buccal samples, then only a performance check is necessary. Furthermore, Forensic Standard 8.7 describes that rapid DNA systems have preset default thresholds that should not be changed because typically the system has gone over very intense and extensive validations and development prior to NDIS approval. So typically rapid systems are not, no human intervention is necessary. As a human identification professional services, we do offer a comprehensive service that goes from experimental design all the way to report delivery. So our group has been doing this for the past 10 years with standard CE, STR core technologies, and we offer the same service with rapid technologies as well. So we do work closely with the customer from beginning to end. We start off with a very collaborative, high-level collaborative validation design to make sure that all the studies that are required for the validation are performed and ensuring that the correct sample types are used for the validation. After planning the experimental design, reagents and supplies will be shipped to the lab. All the wet work will be performed on site with the systems being tested. Once all the wet work has been complete, we will take the data, analyze all the data very thoroughly, and write a comprehensive report. After the report has been written, the report will be delivered to you for final reading, as well as any training that's necessary based on the data that's presented. And that is a high-level overview of how to implement what Mark and his team has developed with the Rapid system for your lab. Look forward to any questions that you guys may have. Thank you.
That was great. Thanks, Joe, for discussing implementation of the Applied Biosystems RapidHIT ID system and our professional services offering. Okay, we've got a few minutes left. Mark and Joe, we had a few questions come in from the audience. I will go in no particular order. Feel free to jump in, but maybe, Mark, this one is for you first. So our first question, can any of the thresholds be modified on the Rapid instrument?
No, that is not possible today. Those settings, as Joe indicated in his presentation, where he cited the draft standard, are really meant to be in place for use and to be adopted readily as an expert system by all users, lowering that bar for the ability to more easily validate when these systems are adopted in settings such as booking stations. That being said, however, if you did want to embark on reanalysis, you do have the ability in the secondary analysis software, such as Gene Marker, to modify those analysis settings there and thresholds to make any changes that you wanted to there.
All right. Thanks, Mark. So our next question in sensitivity study, what substrates was wiped?
Yes, so throughout this entire study, we only focused at this point on those cheek swab samples that I defined previously as buccal swabs. So that has been the focus of this study at this point. Additional substrates will be evaluated in additional product offerings.
Awesome. So our next question, does it exist only in one cartridge instruments, or are there also more cartridges?
Sure. So today we do only have the one cartridge available for running samples. We have the GFE or Global Filer Express ACE cartridge, which is all of the results that you saw today. And today's validation focused on those cheek or buccal sample workflow. That isn't when I say that that's our only cartridge for sample testing, that's true for sample testing, but we do have other cartridges with the system. Today you saw results from the allelic ladder cartridges in the precision study. So those are all pre-made, ready to be run on the system, pre-identified by an RFID tag. So the system knows automatically that you're running that control cartridge. Similarly, we have positive control cartridges, which are evaluated against a known genotype to be sure that the system is giving accurate DNA profiles. Also, once again, that's identified by RFID tag. And then finally, we also have negative control cartridges in the system, which do provide the ability for you to assess sample blanks. Once again, tagged by RFID and will be evaluated in the system software to ensure that it does contain no allele calls or a negative profile. In the future, we are also looking at development of additional sample cartridges for differing substrates, such as more in line with crime scene evidence.
All right. I just want to remind the audience that we are taking questions live, so feel free to enter your questions. We're going to get through as many questions as we can. Okay, next question. Has this validation data been submitted for publication?
We do have the validation user bulletin that is going to be released in the next coming month or so. So that will be all highlighted there, where you'll see this data in addition to some other data that I may have not had time to present today. So that is absolutely forthcoming.
Great. So our next question up, how many samples are run in a typical validation study? I think, Joe, this one is for you.
So it does depend on the package and the testing level that you want. For a validation, for HID, typically about 60 to 70 samples, and that's all depend on the type of studies and the data that you want to get out of it. For a performance check is about half as much, so at least about 30 samples. And then the evaluation is even less, about 10 to 20 samples, depending on the known and non-probative samples that the lab wants to test. But because it's a collaborative design, we can definitely work with the lab to see and adjust the number of samples depending on what focus the lab needs.
All right, and then next question, how was your sensitivity study designed? Joe, I think this is another great one for you.
All right, so like Mark mentioned, during their development, they had to make sure that they tested wide levels of buccal swiping. So like you said, they tested 1, 5, 10, 20 passes across the cheek to get an idea what the sensitivity levels of buccal are. So unfortunately, with buccal samples, it can vary from individual to individual, as well as swiping itself can be a little bit variable. So in terms of experimental design, using buccal samples may not be ideal, only because of how variable buccal samples are. So in terms of the validation, we also used saliva samples to control the experiment, the sensitivity experiment a little bit more, just so you can see a nice trend from high levels of saliva all the way down to low levels of saliva. Saliva may not be the intended substrate for the system, but at least it definitely shows the sensitivity trends that we're used to seeing with when we perform standard CE/STR validations.
All right. Thanks, Joe. I think with that, thank you, Mark and Joe, for presenting today, and thank you to the audience for participating in today's session. Just want to remind the audience that we do have a brief survey at the end of the session, so we would greatly appreciate that you take that time to fill that out. And with that, we'll close the session now, and everybody have a great rest of your week. Thank you.